looking at symmetry. This should look familiar from geometry. For instance, in geometry, you may have a pre-image and it may reflect over the y-axis, and then the image would be graphed, and you would have symmetry about the y-axis, because if you were to fold that along the y-axis, it would match, right? Ideally, I know mine's not perfect, but ideally it would fold along the y-axis, and if you think of it as like wet ink, like ink that's not dried yet, it would leave the image reflected on the other side. Symmetry. Okay, well, we're going to look at symmetry in a more mathematical sense. Woo! Instead of, oh, this is where you fold it, this is what it reflected over. We're going to look at the algebra behind the symmetry. First of all, this is just a couple of examples of symmetry in the real world.
It's not me in that beta club induction.
Okay, so go to this slide. You do need a highlighter. If you have a highlighter, it would help.
Yeah, I got pink.
What color?
Yeah.
Let me do one.
Wait, she did?
Yeah.
My turn.
Why are you saying it for Ray?
My turn, my turn. Gotta mix them. Alright, just pick one.
Someone definitely chewed on it.
It was me, Just kidding.
Don't look.
Okay, look at this right here. It says consider the points 4, 2, and 4, -2. They are on the graph x equals y squared. This should look awkward to you, x equals y squared, and that's because it's not a function. We're used to y equals something. You can tell it's not a function because if you look at this picture, it would fail the vertical line test. Notice it says that this is an example of symmetry with respect to the x-axis. Let's take your highlighter and let's highlight where the x-axis is. You may even want to highlight in the paragraph that this is symmetry. Hold on, I'm not on the highlighter. Symmetry with respect to the x-axis. Y'all got jokes. Symmetry with respect to the x-axis. I can't do that. That's double
There's like 45,000 people who just spawned in.
All right. I want you to recall the acronym to help you remember the equations of vertical and horizontal lines. Recall Hoy Bucks.
Are we writing this in highlighter?
Why would you write something in highlighter?
No.
A highlighter is used to highlight things in math. A pen is used to take notes.
Why are you so aggressive?
Let's make this point bigger and this point bigger. What do you notice about the 2 points? Compare them. What changed?
The Y.
The y's sign changed, right? So reflecting over the x-axis changed the sign of the y. This that I'm about to write is exactly what we cover in geometry. You take coordinate points, the arrow means there's a transformation, and then you write the written rule. You just said that x stays the same, y has a sign change. Here's what that looks like as a written rule. X stays the same, y has a sign change. This little negative means opposite sign. Sign change. You can write whatever you want to write. Opposite sign, sign change. So this particular graph is symmetrical about the x-axis, if I wanted you to take it a step further and tell me the equation of the x-axis, you would need Hoy-Vux. It runs horizontal, so it's going to be a horizontal equation, which means it's written y equals a number, crossing where on the y-axis crosses at 0. So the equation of the x-axis is the line y equals 0. There's really nothing new up there. Nothing new necessarily. You learned this written rule in geometry. I'm not asking you to memorize the rule. I'm just saying understand that if it's reflecting over the x, then x stays the same, y has a sign change. This is saying it's symmetrical over the x-axis. This is the equation of the x-axis. I got it by doing Hoy-Vux. The x-axis runs horizontal. That tells me it's y equals a number. The number is where it's crossing the y-axis. It's at 0. Okay? Now let's go to the next slide. And we have the exact same. Is everybody good with that? Can I change the slide? We have the exact same type of problem, but this time it's reflecting over the what? The y-axis. So this one is symmetric to the y-axis. We still have Hoy-Vux to help us. So recall from geometry, if you take any coordinate point and transform it, if we're going over the y-axis, then what do you notice about the points? The x gets a sign change. X gets a sign change. So this particular graph is symmetrical about the y-axis. What is the equation of the line that is the y-axis? It's x equals 0. How do I get that? It runs vertical, so that's Vux. It's going to be x equals a number. To get the number, you go to the x-axis and ask yourself, where is it crossing? It's crossing at 0. Four slides down. 7 to go.
This is easy.
It's not about
Shh.
All right. Next slide is another recall from geometry. Okay.
I didn't ever see this in
That's
the
why I'm helping. Well, that's because you didn't have me.
I had Coach P.
I'm warned. I understand.
Let's look. Please highlight right here that this picture is symmetric to the origin. Now, in geometry, we didn't actually say symmetric to the origin. Instead, we said that you would rotate it so many degrees. I'm really curious to see if you can figure out how many degrees. Look at the picture. How many degrees would you be able to turn it and it would land back on itself?
180.
180. If you rotate an image 180, you are doing the same concept as a symmetry to the origin, depending on where it is on the coordinate plane. So this is symmetric. I'm going to put an X there because that is the origin. That would be like where you hold the paper down and you turn it if you were doing a rotation. To help you see the rotation, the coordinates in quadrant 1 are x, comma, y. If I rotate 180, I'd land, if I was in quadrant 1, I would land in quadrant 3, and I would have the coordinates of what form? Negative x, negative y. Does the direction that you're rotating matter if you go 180? No, not at all. Because if I face one way and I do a 180, that just means I'm facing now the complete opposite way. If I go back and I do a 180 in a different direction, I'm still landing in the opposite direction. So when you're talking about rotating 180, the direction that you rotate does not matter. That's the only one that the direction does not matter. Now, what do you actually need to just recall for a second from geometry? This is just a nice to know, not a must know. It was called point symmetry in geometry. It was when you could hold it down and turn it upside down 180 and it would be the same image. That was called point symmetry. So that graph is symmetrical. When we say with respect, we mean where you're holding your finger down on the paper before you turn it. With respect to the origin. So that graph is symmetrical with respect to the origin. Is that graph a function?
No.
No, drop a vertical line. Right? Does it pass the vertical line test? No. So it's not a function. Okay, so we just covered 3 slides to give you the visuals of when it's symmetric to the y-axis, symmetric to the x-axis, or symmetric to the origin, right? Now we're going to do slides to cover the algebra behind what we just talked about. That's the layout here. So what you just saw is the visual. Now I'm going to show you the algebra behind it. Because what's this class? College algebra. You have 3 types of symmetry. They're the ones we just talked about. You have the x-axis, the y-axis, or the origin. 3 types of symmetry. If you can go back to the visuals and think to yourself what we noticed happened with the points, then you don't have to memorize what I'm about to highlight. If you don't think of the visuals and get what I'm fixing to highlight, then you're going to have to memorize it. You with me? Okay. So let me walk you through trying not to memorize it, because usually when you memorize stuff, things mix up, and then you're in trouble. If I'm flipping over the x-axis, always think of the case that would help you understand it easiest. Don't think of a picture, like red means wrong. Don't think of a picture like straddling the x-axis. Instead, think of a picture where there's something up here, clearly up, and it's fixing to go over the x-axis, so it would clearly land down. That's what you need to think of, and then you'll be able to get what I'm about to highlight without having to memorize anything. All right, so imagine something up. It's reflecting over the x-axis. Ask yourself, what would change in the points? What would change? What? The y changes. If you're testing a function for symmetry over the x-axis, you will simply replace the y with a negative y. And you'll look to see, is it the same equation? And if it is, then it has that symmetry. If not, then the answer is no. If you're checking a graph or an equation to see if it has symmetry over the y-axis, okay, so you've got something clearly here, it's going over the y, it would land clearly over there. Ask yourself what changed. X changed sign. So take x and replace it with negative x. And if you get the same equation, then it has That's symmetry. You're going to see what I'm talking about in a second. If you're checking if it has symmetry with respect to the origin, go back to this. Notice what happened to both of them.
Both would.
They both change signs, right? So you're going to replace both x and y with negative x and negative y, and you're going to look to see, is it the same equation? If it is, it has symmetry to the origin. Okay, that's great and all. Now we're going to actually do it, because I know you're probably thinking, I have no clue what she's talking about. So we're going to test the function, or the equation, y equals x squared plus 2. We're going to test it for all three types of symmetry. So let's make note to ourselves, lay it out. We're going to test the x-axis, the y-axis, and the origin. Okay, they are a little backwards. Like if I'm testing for symmetry over the x, I'm taking y and replacing it with negative y. If I'm testing symmetry over the y, I'm taking x and replacing it with negative x. If I'm testing symmetry with respect to the origin, I'm taking what is normally xy and I'm replacing it with negative x, negative y. Those are your formulas, if you want to think of them as formulas. Now it's a matter of plug it in and look to see, is it the exact same equation that we were testing to begin with? So let's come right here. We are simply going to go in this equation, find y, replace it with negative y. All right? So I'm going to go ahead and replace. I'm making it really bold, or I'm trying to, so that you can see that it's changing. And I'm going to leave the rest as is. See what I did there? I took the regular y, I replaced it with negative y. Now, initially looking at it, I can see that that's clearly not, this is so simple, it's almost, you almost feel like there's got to be more to it, but there's not. I can already see that that's not the same equation, but just to double check myself, I'm going to divide by negative 1 to the other side, right? And is that the same equation as the original? No, totally different. Compare that to the one we boxed in. Totally different. So no, this graph, if you were to graph it, is not symmetric to the x-axis. And if you need help visualizing it, the graph is right here. Here's the graph. Imagine flipping it over the what? X-axis. Would it be symmetrical? When we say symmetrical, we mean, back here, it means that if I folded it along the x-axis, the image matches, right? Well, if I come back over here and look at this, if I fold that graph along the x-axis, it does not match. Now I have a new part down here, right, that was not there to begin with. That's a problem. Do you see that? So that's a visual confirmation that no, you cannot flip that over the x-axis and have the same graph you started with. You have a totally different graph. All right, now let's do the y-axis. Find x, replace it with negative x. Here's where people mess up. X is x squared in the original. So you need to put this negative x in parentheses. Okay, so watch. Y equals parentheses negative x, close parentheses squared, plus 2. This is what I just plugged in. I plugged in negative x. But anytime you plug stuff in, you're supposed to use parentheses. Now, why did I not do it over here? Because it didn't matter. Right? Here it matters. Because what happens when you square a negative? It becomes positive. If you don't put the parentheses there, you're going to get this wrong. This is saying negative x times negative x. That would be positive x squared. Is that the exact same equation we started with? Yes. Visual confirmation. Look at this graph. If I fold it along the y-axis, does the image match the left and the right? Yes. All right, now let's check x and y. Now this one's a little, I guess you could say a little extra, because if you know it's not symmetric to one, x or y, then you know this is going to be, no, it's not possible. But I still want you to practice it. So we're putting in a negative y, and we're putting in a negative x. Right? Right. Well, we're covering symmetry. Hi. Hi, I'm Miss Holcombe. Nice to meet you.
That's the two of our board members. Can we tell them hello?
Hello.
They're like
Wow.
us.
Yeah. This one?
They're my college class, the GNTC.
I was gonna say, y'all are learning something right now I don't understand.
They're working on their college credits.
You need
So.
I guess this group doesn't go over to the contra fair.
I don't know if do y'all have classes over there for another college class? No? It's the second. So y'all do? We'll make sure both. So it's nice. Nice to meet y'all. Okay, so we're going to plug negative x and negative y in. Now we're going to clean it up. Sorry, y'all. I forgot that they were coming. I thought it was tomorrow on Wednesday. You can see right here that this is negative y. It would still be there. We've already talked about how this would be positive x squared. And I don't even need to go any further because that's the same issue we had up here when we already made the decision, no, this is not the same. So no, it is not symmetrical to the origin.
Yeah.
She put on
Hi,
her
this is
phone.
my caller by GTC calling
She's looking at me.
See, we're rocking.
Oh, do these things?
These students go to
It's Miss Weeks.
No.
All right.
And
All right.
the students that ride to the
If you
career
look at this
academy.
graph, focus, squirrel.
Squirrel,
Look
where?
at the squirrel.
Like,
If you take this graph and you turn it upside down, would you have the same graph as what you started with? No, it'd be
Wait, if you
upside
turn it
down
upside
now.
down,
That's the same as reflecting over the origin. Remember we talked about how reflecting over the origin is equivalent to turning 180? So a lot of people do better to just turn 180 to answer that question and try and, I said yes. Oh.
Was that silly?
So if I turn this upside down, I would not have the same graph that I started with.
I guess it
Okay?
made me, I got confused. I thought that when you said turn, it made me think of x-axis.
I know, sorry.
It's okay.
All right,
Did
go
you
to
catch?
this slide. This is the same type of slide. It's just a new equation. I would love for you to try it right now. So this is the one you're testing. You're testing this one. Stay locked in, y'all. We need more time on 2.5 than we do on 2.4.
Hey, we're on track right now.
Are we?
Yeah. I feel great about right now.
Whose track are we on?
Yours.
Oh,
racetrack.
You're off.
Racetrack.
please try this. If you need a reference back to the one we just did to see what to do, then do that. Back to the video. We're checking all three types of symmetry, okay? We're going to plug negative y in. We're going to plug negative x in, and then we're going to plug both of them in. We're trying to clean it up to see, is it the same equation? When you go to plug negative y in, it would look like this at first, right? But then you've got to think about if you take a negative, even if it is a number, but if you take something negative and you raise it to an even power, it's going to become positive. Let me help you out there. Negative y squared is negative y times negative y, which ends up being y squared, right? Negative y cubed is negative y times negative y times negative y, which would be negative y cubed. I don't need to go any further because there's a pattern.
It'd just
The
be
next
waffle.
one would be even, so it would end as positive y to the fourth. So,
She's saying like this.
let me erase that.
Who said consent?
It's on her house for that, ain't it?
So right here, where I have negative y raised to an even power, because this is even, it would end up looking like this. It would become positive.
Shh.
Okay? Now compare that to the original equation. What do you notice? It's the same thing. So is it symmetric about the x-axis? Can you fold it over the x-axis and have the same image? Yes. Checking for y, we're plugging in negative x. So we have negative x squared plus y to the fourth equals 5. That's negative x times negative x, so it would become positive. Is that the same equation? Yes. You've got symmetry over the x and the y. You're going to by default have symmetry over the origin. But looking at it, we've got negative x squared plus negative y to the fourth equals 5. That's an even root, that's an even root, so those negatives go away. And yes, it's the same equation. Okay? That's testing symmetry over x-axis, y-axis, and the origin by algebraic confirmation. Okay? Now we're going to do the exact same thing, but this time it's not just a random equation. Now it's a function. So what does that mean if it's a function?
X dot B.
It's y equals, it's f of x. There's no repeating x values. It passes the vertical line test. So there's a little bit more to it, and then there's also a little bit less to it at the same time. So let me show you. So go to this slide right here. So if you're one of those that likes to compartmentalize like what we're learning, notice this has a different title. It says even functions and odd functions. The difference is we're no longer talking about equations. We're now talking about functions, which means a lot. We're talking about graphs that pass the vertical line test. So before, where we had y, we now have f of x. That's the difference, the first difference. So you'll notice the last couple of slides was y. Now it's f of x. Okay, a couple of things to highlight here. Trying to find. All right. Even functions and odd functions. If the graph of a function is symmetric with respect to the y-axis, then we call it even. So if it has symmetry to the y-axis, it's called even. Symmetry to the y-axis, we call it an even function. If it has symmetry to the origin, we call it odd. What do you notice is missing? Why are we not looking at symmetry to the x-axis anymore? x's cannot repeat. Okay,
Facts.
so
Great answer.
when I said that it has a little more to it, I haven't gotten to that part yet. When I said it also has a little less to it, that's the part that's a little less. Whereas what we just did was 3 types of symmetry when you're just talking about a general equation. Now we're talking about functions. We can only discuss 2 types of symmetry. The ones that would keep it a function. And that would include flipping over the y-axis. That would stay a function. Or flipping over the origin or rotating 180. That would still be a function. Taking a function and flipping over the x-axis would violate the rule of a function. So that's why we don't discuss that. Okay? So let's make a note to ourselves underneath here. Let's put an asterisk and say note. There's no symmetry over x-axis with functions. Now with equations, yes, but with functions, no. Because the x's are not supposed to repeat anyways. Okay, now, the takeaway on this slide is understanding that if it will flip over the y-axis, it's called an even function. If it will flip over the origin, as in turn upside down, 180, it's called an odd function. Let me show you 2 things. Let's summarize. Right here, even function means it has y-axis symmetry. I'm going to abbreviate symmetry. An even function has y-axis symmetry. You will notice at the end of the box they gave us the formula. It means that f of x equals f of negative x. I'll explain that in a second. For right now, write it down. Odd functions have symmetry to the origin and if you need to under that you can write turn it upside down, meaning you know turn it upside down. And the way that you check it algebraically is f of negative x has to be negative f of x. I got you. I haven't shown you why. I'll explain it. It makes sense once I break it down. Let me show you. How are you going to remember even is when it goes over the y, odd is when it goes over the origin. Let me show you. Probably already know where I'm going with the origin. Odd, origin. Right? It has odd symmetry. If I can turn it upside down, holding the origin in place, turn it upside down, it would have odd symmetry. If I turn it upside down and I get the exact same graph. Okay? Now, how are you going to remember even? I always think of the example of the mother function for quadratics. This is the mother function for quadratics. F of x equals x squared. It is sitting on the origin. It is a quadratic in parabola form. It's perfect, like nothing's been done to it. What do you notice the power is? Even. What do you notice I can flip it over and I have the same graph? The y-axis. That's how I remember that the even functions, for example, quadratic has an even power, can flip over the y-axis and it's the same graph. Okay? And then I remember odd and origin start with O. You with me?
Ms. Holcombe, I need.
No. Stay with me.
We don't have that much left.
I really got.
Three practice problems. Oh, you have to go to the bathroom?
Yeah.
I thought you were talking about brain.
No, I need to pee.
So I've showed you the information, but now we need to actually practice it, okay? And the good news is it's the same thing every time, but it's very uncomfortable because you're just not used to doing this, okay? So we have 3 practice slides, and I've copied over here the directions for checking it. If you were like trying to highlight what actually would be helpful here, first you find f of x equals f of negative x. Once you know that, then you check if it equals negative f of x. So, watch. I know at this point you have no clue what I'm talking about.
I'm just gonna keep highlighting.
That's what the motherfuckers should do. Okay.
Hey!
You gotta quit. Alright. Remember on the other slides when we said we're testing x-axis, y-axis, and origin? Remember that? Okay. Remember on the last slide when we said we no longer have 3 things to test, now we have 2. We're testing if it's even or if it's odd. Okay? So let's organize our thoughts. First we're going to check if it's even. Then we're going to check if it's odd. You're going to need the formulas to check if it's even and to check if it's odd. These come from the last slide. They also come from right here. For checking if it's even, this is what the last slide told us to do. For checking if it's odd, this is what, I think it's f of negative x has to equal negative f of x.
Why are we still laughing?
We're not laughing at you. No, it's something else.
Something wrong?
It's something else.
Can't believe you asked.
All right.
Yell
Now
it to
I
a
need
pencil.
you, guys, focus, dial it in. Now I need you to get a colored marker or pencil or pen, or you can highlight and then write over it, or write and then highlight over it. It's up to you. I'm changing colors for a reason. Every time I teach this, people get confused on this part right here. They never know, what am I actually doing with the algebra? So we're going to actually label what you look at and what you do. You with me? You're going to check this, and you're going to do this. I'll tell you what that means in a second. Here, you're going to check this. Here, you're going to do this. When I say check, what I mean by that is you're going to copy it down. And then the do part is where you're actually doing math. With me? Alright, now that you've written it, now watch. How about don't copy anything just yet? Just watch. So that you're not copying something in the processes of while I'm cleaning something up, and then you get confused. Let me move this down. Alright. Okay, I'm going to check this, do this. This means that this function is right here. 5x to the 7th minus 6x cubed minus 2x, right? I've got my eyes on it. I'm checking it. I see it. But this is what I'm actually going to do. What does this mean to do? Make negative. Like what negative?
X.
Like literally look at it. It says plug negative x in. Into the function f. So watch. I'm going to write down. Okay, I'm doing this. What does it look like? It looks like 5 parentheses negative x to the 7th minus 6 parentheses negative x cubed minus 2x. Now I'm going to clean it up using what we talked about on the 2 slides ago. If it's negative raised to an odd power, it comes out what? Negative, correct? If it's negative raised to an even power, it comes out what? Positive. Oh, it's negative x, yeah. Sorry. Right there. Thank you for catching that. Alright, so I'm going to clean it up. Watch. Negative to an odd would stay negative, so this would be 5 times negative x to the 7th. That'd be negative 5x to the 7th. You with me? See how I walked through that? Minus 6 times negative x to an odd power would stay negative x cubed. Negative x cubed times negative 6 would become plus 6x cubed. So see, the x was actually negative, but it's getting multiplied by a negative coefficient, so that's where that plus comes from. And then negative 2 times negative x would be plus 2x. Right?
Yes.
Okay. You just did, now I know you're probably thinking, what did we just do? You just did the right side. Check it with the left side. That's why we wrote check this. Does what you just got check out to match f of x? No, they're totally different equations. Do you see that? So the answer is not even. It's exactly like what we were doing when we checked the equation with the original equation to see if it matches. It's just now we have functions. So you're checking f of negative x after you clean it up to see, does it match? Look at the formula. Does it match f of x? And it does not. They're totally different. Now we're going to do the odd one. Listen, you always want to check even first, because then it takes the first step out of checking odd. Okay? Notice odd has two parts. Odd says take the function f of negative x and check it to see if it matches what you get when you negate f of x. Well, we've already found f of negative x. It's right there. You see, that's why you want to do this one first. So all we have to do is negative f of x and then check it with f of negative x. So watch. I'm going to do this. Negative f of x means negative, copy the function f correctly. Hopefully I didn't mess up. It literally negates every single term, changing the signs. So this would be negative 5x to the 7th plus 6x cubed plus 2x. That is the function for f, negative f of x. And then now, you don't check it with f. Look at the formula. It says check it with this one. F of negative x. Well, that was up here. So does this match this? Yes. So it has odd symmetry, which means if you graphed it and turned it upside down, you'd have the exact same image. The next slide. Check it. Check the even. What did we do on the even? I'm going to leave this up here so you can remind yourself. You're on the next slide. Check the even by doing what? Plug negative x in and clean it up. This ends up being a short problem, so please stay with me. You're checking for even symmetry. because these are being raised to even powers, they end up going back to positive x to the 6th and positive x to the 2nd power. And does that match the function f? Yes, which means it has what type of symmetry? Here's why it's a short problem. If your function has even symmetry, there's no need to check for odd symmetry. Okay? It cannot have both. So,
Yeah, could you not just skip that?
well, the problem is that if the coefficient is negative, you saw in that last one, where we knew the exponent would leave it as negative, but then it gets multiplied by a negative coefficient, which changes it to positive. So I wouldn't rely on the exponents. Yes. Yes, it will. That would mean it would check both of them, and they would both be no match.
Would that be if one exponent is odd and one is
I don't think that
Bernie,